At the heart of every computer lies a simple yet powerful concept: binary representation. All data, from text and images to videos and software, is ultimately stored and processed as sequences of zeros and ones. A letter, a pixel, or a sound sample, everything is converted to binary. This is because computers operate using digital circuits that have two distinct states: on, represented by 1, and off, represented by 0. These states are physically realized by high and low voltages within the circuits, as shown in this square wave pattern. The fundamental building block enabling this binary system is the transistor, which acts as a voltage-controlled switch. By combining transistors, we create logic gates such as AND, OR, and NOT gates that perform basic logical operations. These gates can then be combined to form more complex circuits, including those capable of storing information, such as a flip-flop latch. This latch, built using NOR gates, can hold a single bit of data, either a 0 or a 1, based on input signals. From these basic principles, engineers have built increasingly complex systems over the decades. Early computers used these same fundamental concepts, just with larger components. These fundamental concepts, binary representation, transistors, logic gates, and storage elements, allow computers to manipulate and store information using only two states. Building upon the foundation of binary representation and logic gates, computers organize memory in a hierarchy that balances speed, capacity, and cost. At the top of the hierarchy are CPU registers and cache memory, which provide the fastest access but limited capacity. Main memory, also known as RAM, provides temporary storage for active data and instructions. At the bottom of the hierarchy are secondary storage devices that offer persistent, non-volatile storage with higher capacity but slower access times. Now let's look at how memory is physically organized. Most computers use DRAM, dynamic random access memory, for main memory. DRAM is organized into memory modules called DIMMs, which contain multiple integrated circuits. DRAM organizes data in a hierarchical structure, starting with memory modules. Each module contains multiple chips, which are divided into banks. Each bank is organized as a grid of rows and columns, with memory cells at the intersections. Individual bits are stored in capacitors that must be refreshed regularly, making DRAM volatile, meaning data is lost when power is turned off. Unlike volatile memory, storage devices retain data even when the power is turned off. The two most common storage technologies today are hard disk drives, HDDs, and solid-state drives, SSDs. Hard disk drives, or HDDs, use magnetic platters with mechanical moving parts. They offer high capacity at lower cost, but with slower access times. Solid-state drives, or SSDs, use flash memory chips with no moving parts, providing faster performance, lower power consumption, and better reliability, though typically at a higher cost per gigabyte. Let's look at how computers process data using the Arithmetic Logic Unit, or ALU. The ALU is a core component of the CPU that combines circuits to perform math and logical operations. The ALU consists of circuits that perform arithmetic operations like addition and subtraction and logical operations like AND, OR, and NOT. It uses multiplexers to select between different operation types based on the instruction being executed. The ALU works directly with data from memory, performing the computational heavy lifting that enables all computer processing. As global data generation continues to grow exponentially, researchers are developing revolutionary new storage technologies. Let's explore some of these cutting-edge approaches. DNA data storage encodes binary information in DNA sequences, with the potential to store exabytes of data in just a gram of DNA. This technology could preserve data for thousands of years. Other emerging technologies include quantum storage, which uses quantum states to store information, holographic storage that records data as patterns of light, and advanced distributed approaches like cloud and edge storage. Finally, let's examine current trends in storage technology. As of 2025, global data generation is approaching 180 zettabytes, with over 60% of corporate data stored in the cloud. Artificial intelligence now plays a crucial role in managing data, automating tasks like tiering, migration, and security. Interestingly, about 60% of all data is considered cold storage, meaning it's rarely accessed but still needs to be preserved.